All right, good day to everyone. This is our lecture on the tutorial of Modflow program. Right, again, this is Rico de la Peña, your part-time professor in Geo 141. Right, so let's first introduce the lecture. Now, what would be your motivations for learning Modflow? First, Modflow is an industry standard software, so this is being used in the private industry, the government, the academe. And in fact, there are a lot of commercial GUIs or user interfaces that are made for Modflow. And these are typically your expensive software that's basically just a GUI so that it's easier to use Modflow. And so that shows how popular the program is. Now, there are other aspects regarding Modflow. It's also a comprehensive program. You can basically do everything that's related to hydrogeology, like groundwater recharge, interactions between the surface water and groundwater. You can also basically model contaminants through the related programs. You can also model saltwater intrusion and also land subsidence and aquifer compaction when you're having an overuse of your aquifers, as well as tools that aid us in groundwater management. Now, there are also interesting developments in the program itself, namely the Modelmuse or the new free GUI of the program. So that's what we will be using for this tutorial, the Modelmuse program. As well as you also have advanced features like Python programming language interfacing and other advanced hydrogeologic modules. Now, please understand that Modflow is, I mean, properly learning this program will probably take a whole course, if not a whole year. And this lecture will obviously just cover the basics, right, and some nifty tricks and features of the program. And the content of this tutorial is just based on the USGS example and Technical Manual 6-A16, as well as the video tutorial provided by the Hatari Labs. But this is not an exact reproduction of those tutorials, so I also added a few corrections regarding the model. Now, Modflow and Modelmuse. So, what are these? Who are they, or what are they? So, Modflow is the code, right? So, back in the days, people used Modflow by working out input and output text files and then running it to the code or the Modflow code without a GUI. So people back then had to do a tedious job of figuring out the input and output text files. Or the other people just bought a commercial GUI to operate Modflow in a more convenient manner. Now, for this tutorial, we'll be using Modflow version 2005. It is not the latest version, sorry. The latest version is version 6, but just for this tutorial, just use the older version because it's more or less it's better documented. Now, Modelmuse is just the GUI for Modflow, although Modelmuse can also be used as a GUI for other USGS programs. Now, the example, just a brief description of our study area. Basically, the key question of our tutorial or the problem is that given an aquifer system that is subject to water well pumping, what will happen to the water surface or the hydraulic head in the area? So remember in the past lectures, hydraulic head. All right, when you're talking about hydraulic head, if you're dealing with unconfined aquifers, the hydraulic head is just equal to the water table. But if you're talking about confined aquifers, the hydraulic head is not equal to the water table, but it's equal to the piezometric level, or the level where the or the potential level of the water, right? Now, let's talk about the information needed to do the model. So basically, we just have to know what is present in the area. Like for example, what is the starting water table level, as well as what are the rates of flows that are involved in the area. Like how fast are the water wells pumping? How much water is being pumped out? Do you have drainages that are taking out water from the site? And how much recharge are you actually getting in your study area? Right? So basically, you just have to know the quantities of these inflows and outflows, as well as the breakdown of their components. You also need the hydraulic properties of your aquifers and other units like your aquitards. And finally, you have to have an idea how long you should be simulating the model. Alright, so sometimes this is a matter of trial and error. Sometimes this is a matter of objective, like, uh, right? Or sometimes you have to run the model for a whole year to determine the annual water budget. Right now, let's talk about the boundary hydraulic conditions. So originally, this lecture was supposed to be about boundary conditions, but find it a bit too abstract or too much conceptual, and it's more practical to talk about boundary conditions in the context of hydrogeologic modeling through your Modflow software. Now, your starting conditions are your water table at your basically your ground surface level, and then you have three aquifers. One is an unconfined aquifer at the top, and below the unconfined aquifer, you have two confined aquifers. Now, your inflows, or basically your inflow is just coming from groundwater recharge at the upper aquifer, right? So this is due to precipitation, although we are, in the model we will be just inputting the net recharge. So meaning we'll be just dealing with the number or the rate of recharge. We don't care about the precipitation or the runoff. We have to uh, factor off those processes. We only need to get the net recharge value. Right, so this is represented by a solid box enclosing the upper aquifer, as you will see later in the model. Now for the outflows, you have three elements here. First is an external flow boundary. So this is in real life could be just the down gradient part of your study area. So this is basically the place where your groundwater flow is flowing out to another aquifer. Right? So this is represented by a vertical plane extending from the upper aquifer down to the middle aquifer. Your second element of outflow are your drainages. So you can imagine these as your drainage canals, or your drainage canals in the surface, and they're basically taking out water from your system, from the shallow areas, and draining it out of your study area. And finally, you have your water wells, presumably water supply wells that are screened or open at your aquifers. And we have three sets of water wells, and they are extracting water at the three aquifers in the model. Other information like hydraulic conductivity will be discussed throughout the tutorial. Now, to visualize your model area, this is a side view of the study area. All right, but in the actual model, this is a 3D rectangle, and the side view, this is not to scale, and you have your five layers, your upper aquifer, right? So your upper unconfined aquifer is partly filled with water, right? So it's not fully topped by the water table. The water table is midway throughout your aquifer. Below it is an aquitard or a low hydraulic conductivity layer, and then you have your middle aquifer, lower aquitard, and your lower aquifer. Right now, your external flow boundaries, you have your red object or red line here, which is your lateral outflow. So this is basically the down gradient side of your model, and this is the where the groundwaters come exiting your study area. And you also have a net recharge in your whole study area, and it only involves your upper aquifer, right? But of course, if you get recharge in your upper aquifer and the upper if the upper aquifer is hydraulically connected to your other layers, the other layers will of course also get recharge. And then you also have your water wells. You have three sets here. All right, so one in the upper aquifer, and this one is screened to the upper aquifer, and then another set in the middle aquifer, and then a third set in the lower aquifer. Right now, let's proceed to the modeling. Right now, before we start, these are the stuff that you need. First, you need a Windows computer. You need a WinRAR program or a 7-zip archiving software. The lecture handout, sorry, and then the Modelmuse version 4 installer, which is provided in the message, as well as the Modflow 2005 installer, which is in a zip file, and the example data from Hatari Labs. Now, for the installation, of course, I won't be showing this, but install the Modelmuse through the executable file. Now, once you have installed Modelmuse, you will have to create a folder in your drive C and name it as WRD app. Right, you can see this one. So create a folder, name it as WRD app, and then unzip Modflow 2005 to that WRD app folder. Right, so basically you just unzip the whole Modflow installer in this area, and that should be fine. And then after that, we have to make sure that Modelmuse is correctly locating the program. We do that by opening Modelmuse first. Right, so start Modelmuse, and then you just create an arbitrary model, create a new Modflow model. Just keep on clicking next, just ignore those things. And then go to model, to the menu bar, model, packages and programs. Is that correct? I think that's not correct. sorry, it should be program locations, model, program locations. And you can see here you have your Modflow 6. We don't need it for now. Go to Modflow 2005 and check the location of the model. So it's in WRD app and then Modflow 2005 and then bin folder and then Modflow 2005.exe, right? That should be fine. All right. Now, you can also install other USGS modules. You just have to follow the links and unzip them and then locate the paths of their executables. But for now, we only need Modflow 2005. Now, let's start again Modelmuse. So we have to exit this program. Don't save. So let's just first set up the grid of our model. Right, so create a new Modflow model and then input ESPG of this value. Create new Modflow model, input the ESPG value, and then wait a minute. Input the ESPG value next. Oh, French. And then specify the grid, the number of columns, number of rows, and number of grids. But first, you have to change the Modflow version from Modflow 6 to Modflow 2005. Right, so make sure that is correctly selected. Number of columns is 15. Column width is 5,000. Number of rows is 15, and then row width is 5,000. And then you have 5 layers. Right, and then so we have basically 5 layers representing the 3 aquifers and 2 aquitards. So the lowermost one is your lower aquifer, and the middle layer is your middle aquifer, and the you have an upper aquitard. So upper aquifer, upper aquitard, middle aquifer, and then lower aquitard, and then lower aquifer. Now we have to specify the absolute elevations of these boundaries or layers. Now the model top is basically the top of your first layer, and that is 200 meters absolute elevation, and that is in meters. If you will remember previously we selected units of meters in this project is in meters. Upper aquifer you have negative 150 meters elevation. Upper aquitard is negative 200. Middle aquifer is negative 300. Lower aquitard is negative 350. And lower aquifer is negative 450. Right, so those are your 5 layers. Hit finish. and you will be back again to the Modelmuse interface. Alright, so you can see here, this is your top view of your model. And then on your right is the side view on one axis, and then another side view on another axis. And finally, at the bottom right is your isometric view of your model. Alright? And this view is actually just view of one layer. If you will look at the upper left, you can select different layers in your model. Right? So anyway, so let me right. So this model has 5,000 columns and 5,000 rows, and one it has a width of 5,000 units and row width of 5,000 units, and that is equivalent to 5,000 meters by 5,000 meters. All right, so that's the total length of your study area. Now, 5,000 meters is divided into 15 columns and 15 rows. So you basically have one cell has a measure of around 333 meters per side. All right. Now, now let's first set the hydraulic properties of our layers. So we go to menu model, Modflow layer groups, and then one of the ways of dealing with aquitards or layers with very low flow is to basically disable them in the simulation. So we select the upper aquitard and then we set it to non-simulated. All right. What non-simulated means is that we will be disabling the lateral flow. Right. So you will have a zero flow, lateral flow in this layer, but this will not disable vertical flow. All right. So you can still get flow from your, for example, from the upper aquifer into the upper aquitard. So that is still possible, but you will not be getting any lateral flow within the upper aquitard. So we do the same to the lower aquitard. Click OK, and that's so we have set the properties of the aquitards. Now we set again the hyd- hydraulic property values of these layers. So we go to menu data, edit datasets, and from there you can see required. You go to hydrology, click K sub X or the hydraulic conductivity and the x-axis. And the default formula is 0.0001, but we will be changing this. So instead of having 0.001 for all the layers, we will be specifying different hydraulic conductivities per layer. There are many ways to do that, but one of the ways to define it per layer is to use the logical argument or logical function case. And the first argument in this formula is the index, all right? So in this case, our index is our layer. So we just choose layer. And then from there, we just have to input the hydraulic conductivity values from layer 1, layer 2, layer 3, and layer 5. Alright, so let's start with layer 1, 001. So this is in meters per second. Alright. I will be explaining later on why this is in units of meters per second. And so that's for the upper aquifer. And then for the upper aquitard, we have a value of 1000. But this value is actually meaningless because the aquitard is non-simulated, meaning any value you put for the lateral hydraulic conductivity will always be set to 0. Okay, so if you put 1 or 0, it won't matter. It will still be set to 0 because the aquitard is set to non-simulated. And then we do the same for the lower aquitard, alright? And those are the values we put for all the layers, right? Click apply, and then go to the next hydraulic conductivity, which is K sub y. Now, as you can see here, K sub y is the values of K sub y is shown as the value of K sub x. This means that whatever value you get for K sub x, this will be used for your K sub y. Now this is a valid, or this is perfectly fine because this I mean this is a good this is an acceptable default value. All right, for especially that our example, let's just say flat lying and more or less each layer is homogeneous. All right, so you more or less have a uniform lateral hydraulic conductivity. So let's leave this value alone. Although there are certain cases where there are certain cases where uh, it where the ky is different from your k sub x. For example, if your site has stratifications or layerings that involve lateral changes, for example, facies changes within the aquifer, like the aquifer unit is going from sand and then silt and then clay within the same horizon. And more concrete examples are your buried channel aquifer systems. So in a floodplain, you have your old channels that are acting as aquifers. And these aquifers will consist of overlapping buried channels of silt, sand, and clay. And of course, your flow will always be faster or higher when the flow is going parallel to the channel direction. All right. Now, the other example is in a dipping sandstone mudstone aquifer, you will get a higher hydraulic conductivity in the direction parallel to the strike. Okay, so in general, you can imagine it as this: if the flow is flowing parallel to the layer boundaries, each flow front in each layer is just moving on its own pace, right? So you can basically just average the hydraulic conductivities of each layer and you will get your flow rate. Now, if your flow is actually going perpendicular to the flow boundaries, the whole flow front will have to spend some time on each layer before it can move to the next layer. All right, so if there is a clay layer that's blocking the way of the whole flow front, the whole flow front will have to go through that layer. All right, and in general, we calculate or we take the average hydraulic conductivities of those in those units by taking their harmonic mean, and that will be a lower, and you'll generally get a lower value when you're getting the harmonic mean of your values versus an arithmetic mean. All right. Now let's talk about the vertical hydraulic conductivity. So this is okay. Let's go to the k sub z. And you can see here that k sub z is just k sub x divided by 10. And they're actually, and this is a valid default value actually, because it's actually difficult to obtain the vertical hydraulic conductivity of your layers, right? It's easier to obtain the lateral hydraulic conductivities ky or kx, and sometimes we approximate the kz as ky or kx divided by 10. Okay, but of course the best way to estimate the kz is to just consult literature or textbooks like Willis and Kresick, and look for the relationships between kz and your kx. So for now, for this example, we'll just edit this value, and again just use the case formula. Now case layer, and then we just input the values of kz. So for upper aquifer, you have 1 meter per second, and then for the upper aquitard, we have 1 e negative 6, or that is equal to 1 times 10 to raised to the negative 6. All right. Now for the third layer, which is your middle aquifer, the value is 1. And then for the second aquitard or the lower aquitard, we have a value of 1 e, or 1 times 10 raised to the negative 7. And then the lower aquifer is 1. Now note that while the aquitards are non-simulated, even if the layers are non-simulated, their vertical flows are still simulated. So these values is 1 times 10 raised to the negative 6 and 1 times 10 raised to the negative 7 will be used by the model, unlike in in the ky and the kx. Right? So these values will be used by the Modflow. Right? So apply and the obligatory save. Right? So now we are done with the hydraulic conductivities. Let's move on to the model time. Right, so I haven't saved the file itself, so I have to specify. So let's make a dedicated folder for this model. Right, so we have saved the model. Now let's set the model time, or how long will the model run, or how long will the simulation run. So that's menu model, Modflow time, and then the starting time is 0. And then we will be running the model for 1 day, right? So instead of calculating the day into second, we can just use this converter. So 1 day, input unit is 1 day, input value is 1. output unit seconds, so you get 86,400 seconds. So ending time is that. And then if you will look at the last column, you get a number of steps calculated. You'll get 86,400 steps to be calculated for the simulation. So that's a lot. I mean, hydrogeologically speaking, it 1 day simulation and thousands of steps is a lot. So, and that will also kill your computer. So, you can set that to just one time step. Okay, so just go to this button, just click this F button, set the number of time steps to 1, and leave the period length alone and leave the multiplier alone, alright? So that you will get a number of steps equal to 1. Now you can also change the time unit, but it's not advisable, and I will show you why. So changing the units from seconds to days will affect on how the Modflow interprets your units of measure. So earlier we input, for example, 1 meter per second hydraulic conductivity. If we change that to days, the time units to days, the Modflow program will now interpret that as 1 meter per day. So it's just best to stick with the original time units that you're using. So let's stick with the seconds. And that should be alright. Now let's move on to activating the relevant module packages. So as you will see, Modflow is composed of different modules or packages, and you have to activate them individually because, I mean, first to save computational time, right? You can't make the model run all the modules at the same time. And another, of course, is the outputs, right? So to avoid cluttering the model with so many outputs that you don't need, you are more or less forced to manually select all the relevant Modflow packages and programs before you start the model. Now, first is the flow packages. Select the LPF or the layer property flow package. And then for boundary conditions, select specified head CHD. And then boundary conditions, specified flux, select RCH and well for the recharge in the well packages. And then for boundary conditions, head dependent flux, choose the drain package. All right, so those are the packages we need: the LPF, CHD, RCH, well, and DRN. That's all right. Now let's move to the drawing of the lateral outflow boundary. So remember that this boundary is the outflow boundary, and this will only cover the upper aquifer and the middle aquifer. Now, to start, we draw a line. You do this by clicking the Create Polyline object in the menu bar icons. So click at the center of the cell, and it has to be at the center of the cell so that this object will influence the cells that are intersected by the line. And then double click at the end of the line, and then the properties of the object will automatically show up. Now let's rename this object as head underscore 0, and then change the model coordinates to model top for the higher z coordinate, and then middle aquifer bottom for the lower z coordinate. So you can find that in the datasets required layer definition, middle aquifer bottom. Right, and then before exiting this, we have to define, of course, the Modflow feature of this object. Right, so this is an external boundary, so you just have to specify its hydraulic head. So this boundary has a constant hydraulic head of 0. So meaning its hydraulic head or water table will be forced to reach 0 meters elevation or sea level. So throughout the model, from 0 to 86,400 seconds, you will have a starting head of 0 meters elevation, and then the ending head will also be 0 meters elevation. So that head will stay constant throughout the model, but you can also specify it to change, for example, to 5 meters elevation at the end of the model, and the model will just try to fill up or interpolate the changing heads throughout the simulation. But for now, we only need 0, so just set that to 0 and we're fine. That should be fine. Alright, so CHD 0. Okay, now let's input the recharge boundary. And basically, we want to apply recharge on the whole upper aquifer. And we do that by applying or drawing a rectangular object. Alright, and this is the property of that rectangular object. Rename it to recharge. And then set the z formulas to 0. Alright, so it will only affect the upper layer. You can see here, higher z coordinate is model top, and the lower z coordinate is the upper aquifer bottom. Alright, so this recharge object will only affect the upper aquifer. And then we set the mod flow features, check the recharge package, and then we just set a constant recharge rate in this object, and that has a value of 3 times 10 raised to the negative 8 meters per second. Alright, so this is in units of meters per second, right? And that is occurring at the upper aquifer unit. Alright, now we will be proceeding to adding the well objects. So first we have to hide all the existing objects so we can easily place the well objects. Now we will be adding 3 sets of wells. The first set will only cover the upper aquifer, and this will be located in the first well will be located in column 8, row 9. And note that you can always uh, determine the location of your point in the model by looking at the status bar below. So as I move my mouse, you can see the column number and the row number below. So column 8, row 9 is around here, this cell. So this is column 8, row 9. right? And you will get properties. So let's name this as well 1, layer 1, and then the coordinates. Okay, so the higher z coordinate is model top, and the lower z coordinate is the upper aquifer bottom. So this is okay. Now we move on to the Modflow features. Just select the well package, and you will basically have a pumping well that is continuously pumping out water out of the upper aquifer at a rate of 5 cubic meters per second. Right, so you have to select pumping rate interpretation as direct, so you can specify directly the cubic meters per second, and you just input a negative value for outflow. So this is an outflow, so you have to put a negative value and negative 5 cubic meters per second. That's all right. Now, since this is a group of 12 wells that are residing in the upper aquifer, instead of repeating the process, we can just more or less clone this well by using the add point section. So you go to the menu bar, object, edit, add point sections, and then we just add well points one cell apart to the right. Right, so add three more well points, and then this is one row. We add two more rows below that are spaced 1 meter apart. Right, so now you have 12 well points in your aquifer 1. You can check this object by clicking the select objects icon, double clicking the wells, and you can see their name, their Modflow features. So they have a rate of 5 cubic meters per second. All right, so that's fine. Now we move on to the next aquifer, which is the middle aquifer. We can do this by selecting. So go to the upper left icon of the model and click the middle aquifer. So this is the upper, then the aquitar, then the middle aquifer. And before that, of course, we can also hide first the objects, hide all objects, and go again to the create point object and insert a well point at column 6 row 4. So column 6 row 4 is here. Right, so we can name this as well 1 layer 3. Alright, and then the upper coordinate is the upper aquitard bottom, and the lower z coordinate is the middle aquifer bottom. Right, so this means that this well is only extracting water from this aquifer, from this layer. All right, but in real world, of course, this well is intersecting all the layers. But of course, this will only be screened or open at the middle aquifer. So it's only extracting water at that layer. Now let's define the Modflow features. Check again the well and just use the same values for the other well. So set, set this to direct pumping rate and input negative 5 cubic meters per second. And then again, we propagate this well by using object, edit, add point sections, and then insert it at column 12, row 6. All right. Now we can check again this pair of wells by selecting them. All right. So that's all right. And sorry. So if you double click them, the properties will show up. So it's in the so it's located in the middle aquifer. That's all right. Pumping rates are fine. Now we move on to the last set of pumping wells. So we hide the objects again, and you can just select the lowermost aquifer here in this icon, and then add another pumping well at column 11, row 5. Right, so we just name this as well 1 layer 5. And this will be located at the lower aquifer bottom and the lower aquifer bottom. Right, so that makes sense. You go on to the Modflow features. Again, just use the same set of parameters. Changes to direct and use -5 cubic meters pumping rate. And you have all your wells in your model. Now we can just show again all the objects by going to object, show all objects, and just right and just visualize the pumping rate. So you can click the data visualization icon, and then in the dataset or boundary condition, you can just click the drop down menu, look for the well pumping rate, click the well pumping rate and apply. And if you will increase the isometric view, you can see the different wells. So this is your upper aquifer, and you can see the 12 wells that are present. And this is your external flow boundary. And then you can still see the upper aquifer, but you can see here the middle, the aquiclude. So you're basically looking now at the aquiclude, and then the middle aquifer, and then the lower aquiclude, and this is the lower aquifer. So yeah, so you can actually see the whole model actually in the isometric view, but selecting different layers will just highlight different layers. Right, so that's a correction. Sorry for the misinformation earlier. So the isometric view is actually showing you the whole model, but you can just highlight specific layers. Right now, so that looks good. Now I'll be just demonstrating another feature of this Modelmuse program, which is the ability of the program to read text input files. So we go back to the RAR file from the Hatari Labs. So it's a RAR file, right? So we just unrar the whole folder somewhere. So I have already extracted it, so I'll skip this part. But this is the data folder that came from Atari Labs. So just open the example problem, Modflow Modelmuse, and then open the text folder, and open the drainage folder, which I think this is a Portuguese word for drainage. So once you open the notepad, you will see a code, and these are just describing the shape and the properties of a drainage system. All right, so you have basically drainage holes that are ultimately connected to a drainage canal, right? But I'm too lazy to read the whole code, so we just select the whole text and copy it. So copy the whole text, go back to Modelmuse, and paste the code directly. And you will see that pasting the code automatically adds new elements to your model. Right, so these are your drainage canals. So you have your outlets are here, and finally, this is the drainage uh, channel that is going out of your model. So it ends up here, and the next cell is basically just your outflow boundary. So the water is going from all over the model, draining out to your drainage holes, and it ultimately goes to this drainage channel, and this drainage channel out will just channel out the water to your outflow boundary. So I hope that makes sense to you. So again, obligatory saving of the project. Now we can now run the model, but first we have to set the mathematical aspect of the model. So go to model, Modflow packages, and programs, and then we go to the solvers, select SIP, and if you will maximize the menu, you can see different different numerical parameters that you can set. Now, so this is just a tutorial. I won't be discussing or teaching you how to obtain all these numerical numbers or numerical parameters. It's best to consult the Modflow manual for the optimal uh, numerical parameters in solving the groundwater flow equations. But for now, let's set maximum number of iterations to 50, number of iteration variables to 5, acceleration variable ACCL to 1, H close to 0.001, so that's fine. Set the IP calc to set by user. Set the WC to 0.001, and then set the printout interval to 999, so that's alright. Right, so again, obligatory saving. And at this point, we can just run the model. So click the run Modflow icon in the menu icon. And then you will be prompted to save or name the out the output file name. So that's problem.nam. So that's fine. And then the model will run. Right, so you can see here a pop-up showing the model monitor, and I'm seeing more or less happy faces, meaning the model run went out smoothly, so the results are consistent. And then you also get an automatic pop-up of a notepad named problems.lst or problems list. So this will just show you the summary of your results. And you can just scroll down to the lower part, and you can see here the volumetric groundwater water flow budget for the whole project area. And I would like to show you two main columns here, the cumulative volumes and the rates for this time step. So the cumulative volumes are showing you the total volumes throughout the whole simulation model. And then the rates are expressed in volumes per time. So L here is the units of length raised to the power of 3. So the units of length here is meters. So so the volumes here are in cubic meters, while the rates are expressed in cubic meters divided by time. So our units of time here are in seconds. So you have cubic meters and cubic meters per second. And finally, you have important rows here. You have your in row and your out row. Your in are your inflows, and this is basically just the recharge. So you only have one recharge process in the model, which is the direct recharge of the upper aquifer. And I'm getting here a value of 157, all right, cubic meters per second. And then the outflow, you have different components. So you have constant head, you have your wells, your drains. Now your constant head is your external boundary that is set to zero to have a piezometric head of 0 meters elevation. So it is just constantly draining out water because it is forced to maintain a constant head of 0. Right? So it's just constantly draining out water from your system, and it's draining at the rate of 65 cubic meters per second. Now you also have your wells, your pumping wells. You have a total of 15 wells that are draining out water at the rate of 75 of 5 cubic meters per second per well. So multiply it by 5, you have 75 cubic meters per second of outflow from your water wells. And finally, you have your drainage canals, which are basically just maintaining the water level in their locations. And in order to maintain the water level in their locations, they have to drain out a rate of 16.94 cubic meters per second. Right, so that summarizes the results of the simulation. Now, finally, we can visualize the head contour of our model. All right, so you can just click the data visualization icon. Oh, sorry, this is the wrong one. You just have to click actually the import and display model results. So click that, and you will be prompted to select between three files. So we just select the FHD, open that, and you basically just have one result to visualize, which is the head. And this is the head of your model at the end of the simulation. So you can display it either as color grid, as contour grid, or neither. So let's just select the contour grid. Okay. And there you can see the contours in the top view, in the side view, and in the other side view of the model. So from the top view, these are basically your water table levels. Or yeah, because the upper layer is mostly just unconfined aquifer. So whatever your head elevation is, that's just your water table level. Now you can also check the the hydraulic heads at different layers. So they're basically changing. And basically as you reach unconfined aquifers like the middle aquifer, the head the head values that you're getting are basically the piezometric levels. All right. Now, let me discuss quickly the output here. So you basically have your higher water tables at the northeastern part of your site, and then you basically have almost zero water table levels near the external flow boundary. So that's quite easy to explain. So your external flow boundary is just continuously, it's just forced to maintain a hydraulic head of a water table of 0 meters elevation. So we specify that in the model, so it's just continuously consuming the water in the side. So it's pulling the water towards the side, and you get a more or less the trend of the groundwater is it's down gradient towards this external boundary. Now you can also see the drainage canals influencing I mean, in a local manner, it's just influencing the water table. All right, so it's forming something like a channel. So you more or less have water here that's draining out to the side. It's so the water here is just sinking locally and draining out to the drainage channel and then exiting through the external boundary. And finally, you have your 12 wells in the unconfined aquifer that are causing drawdown, all right, and the unconfined aquifer. Right, so you can interpret a lot of stuff from this model. You can see the drawdown, you can see the hydraulic gradients developing in the models. You can also see the different piezometric head in the confined aquifers. Right, so that ends the tutorial of this model. So I hope you learned something from this tutorial. All right, let's. All right, so for further learning, you can basically just explore the built-in examples and documentation in the Modflow and Modelmuse program. So if you just open their program folder, you will see a lot of documentation and examples that you can practice on your own. All right. And you can also visit the Atari Labs YouTube channel. So it has a lot of tutorials for the Modelmuse and Modflow programs. Right. So I hope that helps you with learning and appreciating the Modflow program and the Modelmuse GUI, as well as more or less grasping the concept of boundary conditions. All right. Thanks for listening.